Today we want to talk about some words that you can use to make sense of what properties of a function would be. So this is some vocabulary that'll help. Usually this will be for functions in the algebraic sense. These will be properties that you can use to consider what the graph of the function is. So let's think about a situation where a function is defined on an interval on the x-axis. So a set of values that arise on the x-axis will be values that could be used as the x values for the function. And what I'd like to consider first of all is the situation where the graph of the function has a steady rise from left to right. For that to happen, that means that as you go from a smaller x value to a larger x value, from an x value at the left to an x value to the right of that, then the function values are also rising. So bigger x's this way means bigger y's this way. The shape of the graph is generally upwards, and a function like that on that kind of on an interval is called increasing. The other version of that, the other way, would be if it's decreasing. It's decreasing if an increasing x value, a larger x value, leads to a smaller function value. So going from left to right makes the function values fall. That's what's the significance of this inequality. And if that happens on that interval, the function would be said to be decreasing. Certainly, a function on a given interval doesn't have to be increasing or decreasing. It could be going up and down, in which case neither one of these definitions gets satisfied. Or it could be constant. It could be just flat. And if that happens, that's another interesting feature of the graph that you might like to note. Here's an example, one of these screwy functions defined by just looking at values given by a graph, and you can watch them as the domain of this function goes from 0 to 10. You watch as the x values go across that it's rising, it's falling, it's constant, so that you could classify intervals in the domain of this function for those different behaviors. Here's the interval from 0 to 2. On the interval from 0 to 2, we're watching the function values grow from -3 to 3, so that it's increasing on the interval. Notice you give it on the interval of x values from 0 to 2. Then you look from 2 to 7. It looks like there's two different behaviors to the graph. It's doing one thing and then it's doing something else, but it is still decreasing on that whole interval. So you could summarize that on the interval from 2 to 7. Notice again it's an open interval from 2 to 7 that the function is decreasing. And then the last thing to note, a feature of this graph is that from x equals 7 to x equals 10, the function has the constant value. You would say f of x equals -3 for any x between 7 and 10. So you could say that by saying that the function's constant on that interval. Notice that the convention for these definitions is that you're talking about increasing, decreasing, and constant on open intervals. So what that means is you don't care, or you don't specify in saying that the function's increasing, decreasing, or constant. You're not saying anything about what the particular function values are at the endpoints of the interval. The open interval indicates that the x values are strictly between the left-hand endpoint and the right-hand endpoint, and what the definition says is silent about what happens at the endpoints. Okay, so quite often if you've got a function, you would be especially interested in finding champion values. What's the biggest it can be? What's the smallest? It's kind of like the Guinness Book of Records approach to classifying function properties. So let's consider a situation where a function has a largest possible value that would be a local maximum, and the largest value is relative to a neighborhood of where that maximum happens. So if you look at an interval containing C, maybe a small interval a little bit to the left of the x value C, a little bit to the right, and if in that interval you never get a larger function value than the value that is attained at C, then the words would be to say that we've got a local maximum, and the value of the function at that point is the local maximum. So let's keep track of making sure we say it right. The local maximum at C, so this C is the x value, what you're plugging into the function, and the actual local maximum of the function is the function value itself. So the local maximum is the largest the function can get, and if you need to know where it happens, you'll say at that point. Okay, a dual notion, local maximum. If there's local maximum, it makes sense to talk about local minimum as well. A local minimum happens if the value of the function in the interval is never any smaller than at C. So the x value, the value you're plugging in, is the local minimum if the function value at that C happens to be the smallest it can ever be on that interval. And if that happens, then that's where you find the local minimum. How about properties of symmetry? A function's even if it has symmetry with respect to the y-axis. Now you can capture that in this algebraic condition. Symmetric with respect to the y-axis means you go to the left or to the right. If you're going to the right, you're going out x units, and if you're going to the left x units, that would be minus x units. Symmetry happens if it doesn't matter if you go to the left or to the right, x or minus x, you get a function value matching either way. Function's odd if the matching isn't like that, if it has a negative in front. The negative significance is that where a function value has one sign, say it's positive, then the function value for the mirror image point, x compared to minus x, the function value at minus x, is the negative of that. So a typical odd function would be over and up in the x for the positive direction, back and down in the negative direction. So let's capture that symmetry in terms of the shape, the geometry of the graph. A function's even if and only if its graph is symmetric with respect to the y-axis. And odd, the word is it's symmetric with respect to the origin. As I was saying, for an even function, over and up, back and up. For an odd function, over and up, back and down. So you can decide if a function is even, odd, or neither by testing algebraically for the symmetry if you know what the equation is. For example, let's set up a series where we'll look at whether we've got an even or an odd function or neither. Here's an example. G of x is minus z squared plus 2. Let's decide if that is even or odd or neither. What we'll do is compare the graph of g of z with the graph of, or with the values g of z with the value g of minus z. So plugging in minus z for z, everything looks the same in the rule. You could go take it apart word by words. G of z is square z, change the sign, add 2. So g of minus z is square minus z, change the sign, and add 2. So minus z squared is z squared again. What that means is that you could take g of minus z and simplify that algebraically so that the value matches what you had for g of z. And since those two match, that's enough to claim that g of z is equal to g of minus z, and therefore that is an example of an even function. The graph is symmetric with respect to the y-axis. Another example, how about f of x is minus 4x to the fifth plus 3x? First test would be to see if that is an even function, so you could compare f of x with f of minus x. Do that by replacing x by minus x and seeing how it simplifies, and you'll notice that since it's to an odd power in both terms of the function, raising minus x to that odd power changes the sign. So instead of minus 4x to the fifth, it's 4x to the fifth. And instead of 3x, it's minus 3x. Well, they don't match. F of x and f of minus x aren't the same, and therefore it's not an even function. On the other hand, if you look at what minus f of x is, minus f of x is minus that quantity that we had, and if we change the sign back in each term, we're back where we started. So minus f of x and f of x are the same, and that's the condition for an odd function. The graph is symmetric with respect to the origin. So functions can be given, as we've seen, by just giving what the graph is, or a function could be given by an algebraic condition satisfied by all values of x in some natural domain. How about a situation where we'll define a function algebraically, but we'll let the rule change bit by bit? I have in mind a situation for what are called piecewise defined functions. More than one equation, the only way that can work is if different equations apply on different intervals. So here's an example, a function, and now this bracket here is going to give a set of conditions that we'll use to say what function values are different places. So I'll go from minus 2 to 1 for x and have one rule. At the point x equals 1, I'll have a different rule, and at values of x bigger than 1 on that interval, I'll have yet another rule. So with this setup and these non-overlapping intervals, I've got an unambiguous way of specifying what function values are. I sort things out by where the x value lies first, and then see how to apply the rule that goes with that interval. So let's go through some things to do. Let's find some specific function values, find the domain of the function, graph it, and then use the graph. Look at that to see what the range of the function is. So to get that rolling, let's see, f of minus 1. Well, let's see, check which interval minus 1 is in. Minus 1 is between minus 2 and 1, so it's in this interval. That means this first rule applies. So f of minus 1 is x equals minus 1 in this expression, simplifies to 2. F of 1, well, this is a single point defining for x to say that the special value of the function there is at 3, so that's the value that's reported. And f of 3 is in this last interval, so when x is 3, minus 3 plus 3, minus 3 plus 3 is 0. So we've got specific values reported. Let's remember those. Minus 1 gets 2, 1 gets 3, 3 gets 0. That might be useful to know in what the graph of the function is. So remember what the function was. The domain is going to be the x values that work. Well, we're specifying what x values are from minus 2 to 1, also at 1, also bigger than 1. So every x from minus 2 up is a value that is assigned a function value by one of these three cases. So overall, the domain is the set of all x values that work. Everything bigger than minus 2, bigger than or equal to minus 2 works. Here it is in set builder notation. Here's the domain in interval notation. Now let's look at what the graph of it looks like. Since the function was defined in three cases, The three cases are specified by saying that the graph shows up in pieces. This is the significance of it being piecewise. F of x equals x plus 3 minus 2 less than or equal to x less than 1. So I'm looking at x plus 3. That's the graph of a function with slope 1 and y-intercept 3. And it starts at minus 2, goes up to and not including 1. The less than 1 shows up here with the open circle. So this piece of the graph corresponds to that linear function. X equals 1, y equals 3. X equals 1, y equals 3. Here's a single point that corresponds to this case in the function definition. And when x is bigger than 1, we're going to go along the line minus x plus 3. 3 is the y-intercept of that slope minus 1, so it would look like a line that comes down like this. We're only going to draw it in for the relevant part of the domain of this function, x bigger than 1, so minus x plus 3 is defined for x bigger than 1. You can recover those points that I told you about. At 0, it is 3. At 1, it is 3. And at 3, x is 3, the function value is 0. So we were just, for that earlier part A of this problem, we were just zeroing in on particular function values. And of course, from the graph, you've got all the function values you can look at. Now, the last thing that we wanted was the range of this function. And the range is the set of y values that work. Well, I see the largest y values are approaching this open circle here. So the y values that work go up to the y coordinate of this point. That looks like 4, but not including 4. And down, any y value less than 4 works either on this branch or going on down to minus infinity on this branch. So the y values that work overall are anything from 4 down, not including 4. And that would say the range then is y less than 4. Here it is in set builder notation. Notice that strictly less than is needed. Here it is in interval notation. The open parenthesis here shows that point 4 is not included. Okay, I'd like you to give a try to some of the homework problems on what these words describing functions look like. From a graph, you should be able to pick out a local maximum or local minimum, and from a piece-by-piece definition, you should be able to put together what the graph of a piecewise defined function is. So give some of these a try.